Hello and welcome to another edition of Ontology Talk. I'm Adam Pease, and today I'd like to talk about my notion of what is semantics. And semantics is really about the meaning of meaning. And to set the stage a little bit, there are lots of different senses of what semantics is. In particular, linguists have a certain sense of that. I'm really going to be talking about formal semantics, the semantics of formal computational systems, and not linguistic semantics. So semantics is also quite closely related to semiotics, or a theory of signs and symbols. So let's take a look initially at static signs, so signs that don't change. If I'm a driver and I come to an intersection and I see a stop sign, then I have an interpretation of what that sign means. It's a command, essentially, that has some force of law as well, that I have to stop at this road intersection, and after I stop and look around and make sure it's safe to proceed, then I'm free to do so. So there's an understanding of this symbol by an agent. The agent responds to that symbol and has a response that has some significance in the real world. If I come to a sign, however, that I don't understand, maybe it's a sign printed in Russian that may, under some circumstances, mean exactly the same thing, but if I don't understand it, it's no good. It doesn't do anything for me, and so I can't take action according to that. An important thing is that the symbols conform to our understanding of what they mean, and if we have a system that uses those symbols, and the system is not a human, that the system should also have this same understanding. It's essentially performing a simulation of how the real world should act, so that it can predict something that's useful to us as human beings. And mathematics is exactly one of those systems. So we have basic symbols, the symbols for numbers, the arithmetic operations, and so in a mathematical system we expect 2 plus 2 equals 4, and that conforms to what we know about the real world. The operations on these abstract symbols have some predicted value that tells us something useful about how numbers work in the real world, or quantities of things. And we could change these symbols. Of course, there have been different mathematical symbol languages throughout history, if you go back far enough, and we can have different symbols, but that still operate according to the same rules and still have predictive value if we interpret those symbols correctly. So if we have 2 apples, we add another 2 apples, and obviously we get 4 apples, right? So they have these abstract symbols, and they conform to our understanding of how objects behave in the real world. They have predictive value. So if we have a young student in elementary school learning arithmetic, then he or she does this sort of simulation in his or her brain according to these symbols, and the answer hopefully comes out right and conforms to what he or she sees in the real world. And that's how we learn that these symbol systems have value to us. They have utility because they predict something. So we can do these abstract calculations and not have to go around counting apples. We can just use the arithmetic operator to get the right answer and know how many apples we have without counting them one by one, which of course matters if you get more complex operations and larger sets of things. It wouldn't be practical to count 10,000 apples, but if you have 5,000 apples plus 5,000 apples, you've got 10,000 apples, and you don't need to count them all. The symbol system helps you understand the real world. It gives you leverage for understanding the real world. And the same is true in the computer. If you can have the computer understand the mathematics, it doesn't need to understand anything else about the real world. It doesn't need to understand about apples or counting or even really integers. It's performing a simulation that has this same predictive value because it conforms to the rules that we learn in school, the rules of mathematics, and those operations, those symbols, have this predictive value. So there are really 3 things going on here. There are the symbols, the abstractions, there are the reference, the things in the real world, and then there are what those things mean. And it's really this meaning portion of this triangular relationship that we try to get at with the notion of semantics, the study of semantics, creating symbol systems that have predictive value, even though they are just abstractions. So here's another way to look at it. So we have the symbols, plus, to, equals, cosine, any other sort of symbols in a mathematical system or other systems. Of course, there are many such abstraction systems. We have things in the real world: apples, houses, people, atoms. But then most crucially, we have functions. We have a symbol system that can be in a human being's head and hopefully codified, maybe in a mathematics text, where we show that the symbol system is useful and correct and consistent. And we can also program those same semantics, the semantics of the operations and the symbols, into a computer. If we do a good job at that, then we can run things hopefully much faster and with less error in the computer than we could ever run in a human being's head. Now, a limitation of this is that if your symbol system is lacking a symbol, then you've got a problem. There's nothing you can do. Right? So if you want to do a square root operation, you're on a calculator that's a simple arithmetic calculator, and you don't have a square root key, then barring something that like successive approximation, if you don't have logarithms and you don't have the square root key, you're just stuck. You can't figure out the answer. You need a different symbol system and a different simulation of that symbol system, a more complex calculator that actually has this symbol and some semantics behind it, some meaning for that symbol that allows it to do an operation through some means, and maybe it is successive approximation, or it's a logarithmic calculation that will get you the answer for the square root of something. Similarly, maybe you have the right symbols, but your symbol system computation, your simulation, is impoverished. So if you don't have negative numbers and you take 4 away from 2, well, you as a human may know the answer, but your symbol system may not. So your symbol system has to contain the same semantics about the symbols as you have in your head as at least an amateur mathematician or a professional mathematician. And this applies as well not just to formal symbol systems in mathematics, but the representation of all the other sorts of knowledge about the real world. So if we know from, say, some purchasing history that we can say John likes tennis because he bought a tennis racket. But maybe there are other things we'd want to say that are a bit more nuanced than that. Not just that there's a liking relationship between John and tennis in general, but maybe really from his buying history, all we can say is that, well, he must like tennis rackets because he's bought some tennis rackets. Or maybe that he likes just a single tennis racket that he happened to buy. Maybe he's bought more than one. He likes some tennis rackets. All of these 4 things are quite different statements about the real world. And if we want a correct and nuanced or granular view of the world and to have our computational systems share that perspective, then we need a language that allows us to state these very distinct things. If we want our symbol system, our computational system, to have predictive value, then we might want to be able to actually say these individual things and distinguish them from one another. And that's really where the science of semantics, and also in artificial intelligence, where the science of knowledge representation comes in. So I hope this brief introduction kind of made you aware of maybe some of the issues in how we represent systems of symbols and semantics inside a computer. And you might ask yourself, does the language that you've created have all the systems that you actually need? Do you have the systems that tell, the symbols that tell you everything you want to be able to say about the real world? And does your computational system operate on those symbols in the same way that you do? Do you even have a formal system, or do you have just something that's very informal and really relies on the human being to imbue those symbols with some intuitions? If you do, then maybe your computer doesn't have the same understanding. It certainly doesn't have the same understanding as you do if you've never made that explicit to your computational system. As a result, it's going to lack some predictive value. It's going to get answers that you know as a human would be nonsensical. And this is closely related to, is this system correct? All right, great, you've created a system, just like the ancient philosophers started creating symbol systems about mathematics or about logic. And at first, of course, they didn't get these things right. They didn't have a correct or consistent system. So it's no good to have a symbol system and a computational system that imbues those symbols with semantics if your semantics isn't consistent. You want each of the operations that you perform on those symbols within the computational system to yield a correct answer, not to yield something that's inconsistent with what humans know to be true about the real world. And as your symbol system gets more complicated, like all of mathematics, then that takes a lot more work to make sure that in fact it's correct. So if you just as a programmer and you dream up a symbol system on your own and you implement it, maybe if you actually had a way to prove that system computationally, sort of a meta-analysis of the system you've created, it might be the case that it's not consistent. It could get wrong answers. So if there is such a symbol system like mathematics or mathematical logic, you might want to reuse it, because the problem of creating such a system from scratch computationally may be a lot harder than you thought. So again, can you say everything you want to say in the system without relying on a human being to interpret it? If you can't, then you better make sure that you're deriving answers that are presented to a human before that intuition has to be applied in order to interpret the result. And if that's the case, then what's the predictive value of the system? The utility of a computational system and a symbol system or a mathematics is very closely, intimately related to the fact that it has some predictive value. Otherwise, why would you use it, right? If it doesn't tell you something new and informative about the real world, does it faster or more in a more correct fashion, there's no point in using it. So anyway, think about these various questions, and next time you're trying to implement some computational system, and see if that changes your perspective. All right, I hope you found this informative, and thanks for watching.